Pressure, pushing down on me, is a scalar that is defined as force over area. Its SI units are units of Pascal, which are a Newton per meter squared. The English units tend to be pounds per square inch, which you can see a conversion here to Pascal, and there are lots of other units of pressure that have been used historically and are still in use today. You might need to look up some conversion factors dealing with pressure. If you think about pressure, when you have an equivalent force over a larger area, the pressure is small compared to that same force over a very small area, like a tiny, tiny syringe, that ends up with a large pressure. And that large pressure can, in this case, pierce the skin. This is a famous demonstration you can do where you get a bed of nails and you can lay down on it, where a single nail, if you lay down a single nail, it would pierce your skin, but a bed of nails, there's enough area that your force is spread out enough that you don't pierce any given one of them. Don't try it at home. Don't email me if you hurt yourself. Look up a video on YouTube of people not getting hurt. Pressure pushes outward in all directions. Here you see inside of a tire with a valve that you can try and add in more stuff. That stuff is trying to get away from itself. So with gas is always trying to escape there. Anyway, pressure, the force over the area, is exerted equally in all directions inside of a given fluid. Here we have a beaker full of water, and we can think about the pressure as we go deeper in this water as depending on how much stuff is pushing on us. We can say that the mass is equal to the integral of density over the volume, because mass is density times volume in general. And then here, if your density is changing, that's how you would calculate your mass. It's the integral of density dV. If you have a constant density, though, then you just get mass equals density times volume. At a certain depth in this, the weight that's equal to mass times gravity now becomes, with mass equal to density times volume, now we get mass substituted in there, becomes density times volume times gravity. So our weight of our fluid at any given point is density times volume times gravity. The volume here is whatever cross-section area we have times how deep we are in that fluid. And that lets us say that our pressure at the bottom of the fluid relative to our pressure at the top of the fluid is going to be whatever the pressure was out here, plus what additional weight we have of fluid acting down on us divided by that area. This is a way of figuring out how much pressure you get by going deeper inside of a fluid. I've derived it here. We can then say that that weight of fluid is given by this rho AHG, and substitute that in. We'll note that the areas cancel, and we're left with that our pressure at a certain depth in a fluid is equal to our pressure at the top plus rho GH. And we're going to be using this a lot. This rho GH is going to give us the pressure at some given depth h of a fluid. It's going to be the density of the fluid times gravity times that depth of fluid. Let's continue with this and see if we can look at pressure in a static fluid with a little bit more of a calculus bent here as we get, I don't know, well, go with me on this one. Here we have the same sort of setup. We've got a bit of fluid here. Well, okay, the whole thing's full of fluid, but now we're defining this little section here as the differential area that we're looking at. So the differential volume we're looking at. We have some pressure at the top and some greater pressure at the bottom, where force is equal to pressure times area. Pressure is force over area. It's that same relationship. We can then say that the force acting on this section that we're kind of taking out of the middle here, this delta M, this little bit of mass, is going to be the force that's exerted from the bottom acting up minus the force that's exerted from the top acting down, while including its own weight as well. In a static situation where this isn't trying to flow anywhere, our acceleration is 0. And we're left with the pressure pushing up from below minus the pressure pushing down from above and that weight from the mass of the section we're considering has to sum to 0. Okay. We can then rewrite this and say that this pressure at some depth y is that pressure P. So that's this pressure P. And this pressure at some depth y plus delta y is this P plus delta P. So this here was a functional relationship here, where pressure as a function of y plus delta y, and here we've replaced it with pressure plus some additional change in pressure there. Here we've taken our delta m and said mass is density times volume, so delta m is equal to density times delta volume. Continuing on, we can expand this by multiplying out. Group this a little bit differently by noting that our delta v is equal to a times delta y. Because we have some delta y here, we have some area, so our amount of volume we have in this element we're considering is going to be a delta y. And we've got PA minus PA, so those will cancel. We've got now area left on these two, so we can divide everything by area to get rid of that. And we're left with the same relationship we had from the previous slide. So maybe this slide was a huge waste of time. Who knows? Maybe it's kind of redundant. But delta P now, we say our change in pressure just from one to one other side of this tiny little bit in this inside of the fluid is equal to rho g delta y. We can put that on one side, the delta P over delta y, and take the limit as that element gets really, really small. This gives us our relationship dp dy is equal to negative rho g. So we didn't actually have that from the derivation on the previous slide. If you're fine with just believing me that this is the case, that's fine. Here's a derivation to try and justify why this is the case. And what this does is it gives us an ability to say how pressure varies as our depth in our fluid varies based on if our density or gravity is changing as we go. So we can integrate this to get a change in pressure if we have widely varying densities or gravities.